Hello, this is Joe Neville and welcome to this VXLAN Explainer where I'm going to be looking at what is VXLAN, what are some of the use cases that it solves, how to configure it on Aruba networks, AOS-CX, and then we're going to go deep, we're going to capture some packets and really have a look what's going on with those headers. That's the intro, let's dive into it. VXLAN is an abbreviation of Virtual Extensible Local Area Network. It's a way of carrying layer 2 frames over a layer 3 network. Please note, VXLAN is all caps in the RFC, so none of this lowercase x nonsense or any of those other permutations that I've seen, please. It's all caps, we're so excited we're shouting about it. And it is detailed in an informational RFC, so 7348. Now there's not too much in there actually. When that was written, there's a lot of reserved bits in the header. And this has been expanded upon over time with various drafts, including things like I've detailed here group policy. The main point is that the VXLAN header story is an ongoing affair. And that's something I'm going to be looking at later on in this video. What problem does VXLAN solve then? To illustrate this, let's step through some scenarios. So in this simple layer 2 network, I've got a couple of IPv4 nodes. They're in the 172.18.1.0/30 subnet. I've got .1 and .2 over there connected by these two switches, and those switches are just switching frames in VLAN 1, and these are just layer 2 ports. They're going to be access or trunk. Good. But is it? We've only got a single link here, so that's no good for production, is it? Because if that link fails, then we lose our connectivity. What can we do? Of course, we can introduce multiple paths. So we add an extra switch in, but you know, networking basics, what issue does that introduce? Layer 2 loops. So how do we solve that? Introducing spanning tree protocol is one approach, which will block ports there for us so that we only have a single active path through the network, so we don't have our loops. But what issue does that introduce then? Well, we've got redundant infrastructure here that we're not using most of the time. Yes, I do understand that if you're using per VLAN or using multiple spanning tree that, you know, this isn't strictly true, but let's just stick to the real basics and say we've got redundant infrastructure that we're not using most of the time. So it's inefficient and it's costing us money. And another issue with this type of network is that we've got a large layer 2 network here. So, well, it encompasses the whole network as it is. And that means that it has a large blast radius if there are any layer 2 issues, like broadcast storms will be switched around this network. And if you've ever been involved, and even if you haven't, you know, these are bad things. So broadcast storms and spanning tree issues, they're really bad for networks. And thus it's a good idea to keep your layer 2 down to a minimum. And the way that we can do that is deploying layer 3. And in this scenario now, we have a layer 3 core. So we've got /30s between these switches here. So this now is its own layer 2, that's another layer 2 and another layer 2, you know, so we've got a layer 3 core. That now limits our layer 2 with our layer 3 boundaries. So if anything happens on this link, then the frames won't be switched across the network, minimizing that blast radius. But what's an obvious problem here is that the Ubuntu nodes here, our v4 nodes, they were in the same subnet. So our layer 2 has been split by the layer 3 core. So these nodes will not be able to ping each other anymore. We've broken the connectivity. And how to solve that? By introducing VXLAN, we can tunnel layer 2 over layer 3. So if you allow the switched frames from .1 to go over the layer 3 core to .2, and vice versa, you're going to restore connectivity. And another issue that's mentioned in the RFC that VXLAN addresses is scale. Now, if we think about a traditional layer 2 segment, we divide up the traffic using VLANs, don't we? So 802.1q, we have 12 bits for the VLAN ID. That gives us a total of 4,094 possible VLANs. The top and the bottom of the range are reserved. And in a highly virtualized multi-tenancy environment, that's probably not going to be enough. Thus, with VXLAN, they've gone all out with a different identifier to differentiate the traffic. We've got the VXLAN network identifier. It's got assigned 24 bits to it, and that enables over 16 million VNIs. So quite the upgrade in the number of IDs available. Let's focus on the network I'm going to build then. And it is the most basic that I could think of. So it's static VXLAN. And you could say, well, nobody's using this in the real world. And it isn't very popular because static just doesn't scale as well as dynamic. You know, just like with static routes, there's a certain amount of overhead for building the tunnels. Much better to go via a dynamic route unless you're doing very low numbers. But my reasoning here is that with technologies such as VXLAN, which are used with other protocols like BGP, EVPN, creating a kind of protocol stack, it's quite easy to get lost with what's happening at each different level with each technology. In the past, I did a lot of MPLS layer 3 VPNs, and I found that peeling back the layers was the way to really understand what was going on. So that's the approach that I'm taking with VXLAN. I'm going to start with just the most basic implementation, static VXLAN, and having a look at the encapsulation and the decapsulation of the traffic. So here's the network I'm going to configure. I've got a couple of Linux servers. They're Ubuntu here and here. Now, the fact that they're Linux is irrelevant. They could be Windows. The important point is that they are IPv4 nodes. Sorry to all the V6 stands out there, which I normally represent, but this is just a V4 setup. So we've got 172.18.1.1 and 1.2. They're in the same subnet, okay, a /30, and that's divided up by a layer 3 core, which is represented just as this layer 3 link between two switches. So these are Aruba 6300s. I've got -1 and -2 over here, and I've got the layer 3 link is 10.150.99.0/30. And I've tagged that with VLAN 99. Now, these switches act as the VXLAN tunnel endpoints, aka the VTemps. And if you look in the config guides, the VTemps, like the best practice, would be to do it on the loopback, but I've just put it on the layer 3 interface for the VLANs, just making it as simple as possible, I think. So real world, you want to have loopbacks, obviously, so you're not tied to a single physical interface or a VLAN interface. In this case, the loopback always being up unless you configure it as disabled. Now, the other important point in this network is the fact that these segments here are untagged. So they're in VLAN 1 and they have no 802.1q tag against that traffic. And for the purposes of this demonstration, I'm going to start with the most basic, a single VNI. So I'm going to configure the VXLAN network identifier, the VNI, as 1. Let's dive in and get this configured. Here's my demo setup then. I've divided the screen into 4. Top left, we've got my Aruba 6300-1. Top right is -2. Bottom left is my Ubuntu server. It's this node 1 here. And down on the bottom right, I've got a diagram so you can follow along. Let's have a look at the 6300-1. This is the one that I'm going to be configuring. We're running 10.7.4, same on -2. Now, -2 is fully configured. I've already set that up and I've got the VXLAN interface. I'm just going to configure it on -1 here. Thus, this part is configured. I'm going to configure this bit and we're going to send the traffic. And once I've configured this correctly, then the traffic will flow. Fingers crossed. Now, let's show you the Ubuntu server. There you can see the IP address. So 172.18.1.1/30. Let's do that ping. 172.18.1.2. That is failing. Okay. Now, if I show you the config that I've got already. So we've got no VXLAN interface configured yet. I'm going to focus on left to right. So for me, this is the ingress and this is the egress, okay? So .1 to .2, I know it's bi-directional traffic with a ping, but just for the purposes going left to right on the first interface that we'll hit then. So 1/1/20. I've already configured these because, you know, this is the basic stuff. If you're unsure of how to configure this with CX, I'll stick a link on screen now for my VLAN configuration on CX. But there you can see it is a trunk port, but the native is 1. And this is just a standard physical interface that the Ubuntu server's sending from. So it's in VLAN 1, but there's no tag. Okay, so it's a trunk there, but it's hitting with no tag. So it's going into the native VLAN, which is VLAN 1, which is also allowed. The interface that's connecting to -2 then, 1/1/10. Show run int. /1/10. That's a trunk port again, allowing VLAN 99. 99 being that VLAN that ships the traffic across between the VTEMs for us. So that's all configured. And then also, actually, that's already on screen. So you can see that's the layer 3 interface for VLAN 99 that I'm going to use as the start and end point for the tunnel. So the VTEM. Okay. Let's get configuring then, and there's not too much to this. So interface VXLAN 1, the source, I always miss this, you have to put, even though there's nothing else in there, you have to put IP, is going to be 10.150.99.1. I'm going to no shut that, and here we're going to configure the VNI, so VNI 1. And that goes then, as you can see, into a sub-configuration mode for VNI 1. And in here, we tie that to, I'm going to tie it to VLAN 1. And the VTemp peer, because this is static, we're going to statically configure that, is 6300-2's VLAN 99 interface, which will be 99.2, like that. Okay, and immediately you can see that ping is successful, which means that our Ubuntu node here, .1 can ping .2 across the layer 3 core. Okay, so the traffic's coming in with no tag on it. It's being encapsulated for VXLAN, flowing over this link, being decapsulated. The headers are being removed by -2, and then it's being sent on this link with no tag to our destination, and obviously, you know, in reverse as well, which gives us successful pings. Now, there's a number of show commands as well, specific to this. So they're all under show interface. We do a question mark. So we've got VXLAN. There you can see. So show interface VXLAN. If we hit that, gives you a kind of summary view. This is ARP. It's admin ARP. Okay, I'm just using the default VRF. The destination UDP port is the one designated in the RFC for VXLAN. So it's 4789. We've got our source, and then we've got our destination. Not so interesting, but, you know, if you had multiple VTemp peers, these would be listed here. And then we can have a look at, so VXLAN, if we add the suffix of VTemps there, you can see some more information, source and destination. So it presents the information in different ways. And what else have we got? Just going through these. That was VTemps. Let's have a look at VNI. Okay, VNI, fine. So some more information for us there. Moving on and delving a little deeper then. I've logged into both of the Ubuntu servers here, and I've got their connected interfaces. So you can see the MAC address. Now, if we have a look at the MAC address table on our 6300, you can see VXLAN 1 is recorded there under the port. So what's going on here? Well, this is the server that is local to -1. If we have a look at that, so it's ends with C9A1. Which one's that? So C9A1 there, this is the correct MAC, isn't it? Yes. That's the port there, 1/1/20. Okay, this one here. Good. Now, what's the other end? So the Ubuntu Node 2 is this one here, and that is 59A6. So 59A6, and you see that that's been learnt via the VXLAN 1 port there, and you've got the remote VTemp address as well. We can see this on the other end. It will be, that will essentially be reversed. Looks like the pings have timed out. So let's set that ping up again. Finish 2. Okay, off we go. Do that again. There we are. Right. So what do we have? Let's cancel that off. Show that again. So we should see local B959A6. So B959A6 there. Yep, on the connected port 1/1/20. And the remote will be this. So 2FC9A1, 2FC9A1 being learnt via the VXLAN 1 port. And there's our remote vtemp. Okay, now another interesting thing I think is the ARP. Now these devices, they do not participate in the ARP between the servers. They're just switching at that level on these ports. Remember, these are just L2 ports, so they don't actually see the ARP entries for the 172.1.1.0/30 address. As you can see, all we know about is the other end of our layer 3 link. Now, if you look on the servers, you will see that. There you go. So that's the other end. Now, we don't see that up here. I'll show you on this one as well. Show ARP. There you go. You've only got the other end of the link, because essentially on these subnets here, these switches are just acting like layer 2 ports, taking the traffic and then encapsulating it, sending it across the link. Okay, that's the configuration and some show commands then. But to really get to grips with what's going on down at the packet level, I think we need to sniff the traffic. So that's what we're going to do now. I've already configured this, and actually I'm not going to do this live. I'm going to do this with slides to start with, because I've already taken the captures, because I want to mark them up, and my bosses haven't bought me something that I can draw on the screen yet. Hint. So what I've done is I'm using slides, but I think slides is a better way to present this as well, nice and neatly. Okay, so I'm going to sniff the traffic and capture it and then present it at 2 different points. One being this port that's connected to our first Ubuntu server. So this is the untagged traffic coming in if we're going from .1 to .2. I'm going to mirror that and show you what's going on there. So then we can compare that with the traffic that is encapsulated for VXLAN. So the second step is to mirror the VXLAN port, sniff that and present that, what we're seeing from Wireshark. Okay, so first of all, the packet coming in, and here it is. What I've done actually for these purposes, I've upped the size of the ping. So this is the Linux command. I've increased the size of the ping to 100 bytes, pinging the other end of our network, so Ubuntu 2. And so from 100, what you see is that this is what I captured from Wireshark. We see that on the wire, it is 142 bytes. So how does that come about? Well, I've broken that down then. It's the headers, essentially. We've got the Ethernet header there. That's 14 bytes. Then we've got the IPv4 header, and you can see the source and the destination for this is the Linux servers. You know, it doesn't know anything about the layer 2 core and our 6300s. That's 20 bytes. Then we have 8 bytes of ICMP v4 header, and then we have the 100 bytes of the ping. So I've added those up. Ethernet 14, IPv4 is 20, ICMP v4 is 8. That creates a total of 42 bytes of header. We add that to the 100 bytes and we get 142 bytes on the wire. Okay, so that's standard switch traffic with no 802.1q tag. What does that look like when it's encapsulated for VXLAN? So now we move on to mirroring and capturing from this port. So it's quite a bit more, actually. So this is what was presented within Wireshark for a sample packet. And we can see that the 100 becomes 196 bytes on the wire. There's quite a few headers there. So let's step through that. Okay, first of all, and I should say this is divided up into the outer headers, which come down to the VXLAN header there. So the role of these is to get the traffic across this link, and they're encapsulating the inner headers, which are the headers from the traffic flowing across this link. Okay, let's go through them then. I've called them inner and outer. First of all, we have the outer Ethernet header, 14 bytes, and this is a trunk port, so it's VLAN 99. It doesn't have to be, but that's how I've configured it. So we've got an 802.1q tag on there, 4 bytes. There you can see the ID of 99. We've got the outer v4 header of 20 bytes. There it is, and you can see the source and the destination. So that's the configured vtemps. That's these ends of the link. Next up is UDP, and we've got a destination port. So this is the destination port reference in the RFC for VXLAN, and that is 8 bytes. So it's port 4789, I should say. Next up, we've got the VXLAN header of 8 bytes. I'll be going into the details of that on the next slide. And now we're into the inner headers. So that's the inner Ethernet header of 14 bytes, the inner IPv4 header. There you can see that's the source and the destination for the Linux servers, which is preserved and encapsulated. Then we've got the ICMP-v4 header of 8 bytes. And if we add all of those up, it comes to 96 bytes. Combine that with the 100 bytes and you get 196 bytes on the wire. So the high level gist of what's going on is that the customer data is encapsulated to go across the layer 2 and then it's encapsulated again to go across the layer 3. Now let's focus on the VXLAN header, and here it is in all of its glory as presented within Wireshark. Now if we compare this to the RFC, so 7348, this is the VXLAN header from the RFC. And as you can see, there's not really much going on there. So you've got 8 bits for flags, and I've taken a capture. So 8 bits for flags, where the I flag, that's the 5th one, must be set if you've got a valid VXLAN network ID, so a VNI. And the rest are designated as R, so reserved, okay? Now, here we are. So 1, 2, 3, 4, 5. The 5th one is the I flag. The rest are reserved. The rest of this is reserved. This line is reserved. Then we have the 24 bits for the VNI, and the rest is reserved. So there really isn't too much in the RFC that's designated in the VXLAN header. There's really not much to it. So if we map that across, you can see the I flag. Now, I thought this was a bit confusing when I first looked at it, but if you just count across here on this bottom line, it's probably the easiest. So this is the first 4 bits. This is the 5th bit up here, which is set to 1. So we've got VXLAN network ID. The VNI is true. Yes, we've got that set. And also we've got the VNI down there. Remember, I configured it as 1, so that is correct. But that begs the question, I think, what's all the rest of this then? Where's all this coming from? If we've only really got 2 things reserved in the RFC, where is this group policy ID coming from, and this extension or don't learn or policy applied? Where are those documented? Now, I asked that question on Twitter and my boy Alexis came through for me. He did a check and searched on the Git blame actually for Wireshark to find out where that information was referenced, and he posted the link for me. So thank you, Alexis. And that document, he posted the 00 version of a draft document. I've referenced here the latest version, which is 05. What this is the VXLAN group policy option. Okay, so this document here, and essentially what this is, here's a snippet from that. Group-based policy model defines application-centric policy model. So there you go. So it's essentially a way of using some of those flags to carry more information. They're not being utilized in this instance, but Wireshark does display them. Now, here's a capture from that draft document as well. And you can see, so we've got more flags being designated there for the VXLAN group-based policy extension header. And I mentioned, didn't I? So there's the telltale, the don't learn bit is designated there, and we've got policy apply designated there. Okay, so I'll leave the link in the description of this so you can delve into that if you so wish. And what this highlighted for me is that VXLAN is very much not one single implementation. The RFC is only an informational RFC, I believe still. You know, this isn't an internet standard. And doing a bit of research around this, I've found that there are quite a lot of different VXLAN header drafts, documents, etc. out there. I'm not going to go any further into this because I think this is an ongoing process, but if you are looking at VXLAN, so my advice would be keep on your toes. You might see something that you were not expecting, and you certainly shouldn't just be looking at the original RFC. There have been developments in this field, pun intended. Okay, I'm conscious of the length of this video, so to finish up, we're going to do the live capture of the packets. So I'm going to do it exactly like I did with the slides. Here's our network again. I've got 2 mirror sessions. We're going to start with mirror session 2, and that the source interface is 1/1/20. That's that port there. So that's the standard layer 2 frame coming in. Let's set off that ping there. So you can see I've upped the size and we're pinging .2. Here's Wireshark. I'm going to filter on ICMP. It's V4, isn't it? So enter that. Start the capture. Let's grab a few. That should be enough. Okay. Let's have a look at a sample then. Looking at the request. Okay, so it's 142 bytes on the wire. We've got the Ethernet header. We've got the IPv4 header. So the source and destination being that of the Linux servers. And then we've got the ICMP header. Let's swap the mirror sessions. So go comp mirror session 2. I need to disable first. Parallel 1 and then enable. Okay, the ping is still running. So if we start, I think this should be good. Okay, we'll stop that and then grab a request and you can see there we are. So 196 bytes on the wire. We've got the outer Ethernet. We've got the 802.1q ID of 99. We've got the outer IPv4, which is the source and the destination across the link, the UDP destination port 4789. Here is our VXLAN header, as we mentioned before. So we've got the flags there, and this is where, so if I expand that again, here's all of that extra information about the group policy. But what we are interested in is the 5th bit in the flags and the VNI set to 1, the rest is reserved. Then we've got the inner headers, so the encapsulated inner headers, the inner Ethernet, the inner IPv4, and then that's going to be the inner ICMP v4 and all of the customer data. So that was VXLAN Explainer. I hope you found that useful. It was a bit longer than I was expecting, but I'll just push those other tasks into later videos, so please do look out for those, and please do like, comment, subscribe, all of those good things. We really appreciate your interactions, your support and your views. But for now, it just leaves me to say my name is Joe Neville. Thank you very much for watching and goodbye.